Good morning, class. So let's start. It's 8 o'clock. So today we'll be looking into magnetic fields and magnetic forces of current carried conductors and magnetic fields and magnetic forces on current carrying conductors. So we'll be looking at the forces on and the forces of, okay. So we have looked at the electrons many times, or we have looked at electric charges many times, and we've agreed that an electric charge possesses electric field. And once the electric charge is in motion, in addition to its electric field, it possesses magnetic field. We have also defined electric currents to mean the rate at which charges move through a particular cross section. So what that means is that when current, I will say current is flowing, what we mean is that at least charges are in motion, charges are moving. And when charges are moving, then we should expect these charges to have electric and magnetic fields. So when we say current is flowing, what that means is that charges are moving, and since motion of charges implies the manifestation of magnetic field, that means the flow of current should be accompanied by both electric field and magnetic field. So when, from the diagram on the screen, when we assume this gray rod to be a current carrying conductor, and the current flow is in direction I, and we hold the conductor with our right hand such that our thumb is pointing towards the direction of current flow, then the direction of magnetic field can be represented by our other four fingers that curl around the current carrying conductor. So when you hold it with your right hand, such that your thumb is pointing in direction of current flow, then your other four fingers would curl up around that current carrying conductor in a direction that aligns with the direction of magnetic field. So if you look at this, these fingers here, this thumb is pointing in the direction of current flow. At the end, the other four fingers is pointing in direction of magnetic field. So when two current carrying conductors are next to each other, then they experience magnetic force as a result of the magnetic field that surrounds them. So the magnetic field of an infinitely long wire can be obtained by applying Ampere's law, which is defined in this equation. So when we say current is flowing in a wire, we may not necessarily know the length of the wire, but if we say it is infinitely long, that this is very long, such that the length is of not much importance to us. But when it's very long, there are some other effects that may happen at the edges of a wire. But when the wire is very long, those effects will be negligible compared to the effects you will find in between the edges of the wire. So when we have a very long wire, we can break that long wire into small segments. We did something like that, or we spoke about something like that while we're talking about continuous charges. Continuous charges, that is, we're talking about continuous charges. We spoke about the linear distribution, area or circular distribution, and also the volumetric distribution. So a simple trick is when you have a very long material and you want to study that long material in its totality, a simple trick is to break that material into small segments. Then you take each of the segments, you treat them as if they are individual components. Then you now add up the effects you obtain from each of those segments together. So another trick is to, instead of adding them together, you may prefer to use integration. But so summation, so many times if you see summation and integration, most times they go together. If you have a discrete quantity, which you can count easily, fine, summation. But integration does a very good job when you know some properties about some small fractions of a very long item. You can integrate with the knowledge of those small fractions is the dx you have in your integration, the small segments, the dx. So depending on the scenario, there are cases in which it will not be dx, it may be the area, it may be the v, volume. So, but for this case, we are interested in line, the length of the wire. That's why we have delta L here. So the summation of the products of the magnetic field strength and the length, which is also defined as B times, it's like a circumference of a circle. Then we have mu naught I. Well, mu naught is the permeability rather. Mu naught is the permeability of free space, and is defined as 4 times 10 to the minus 7 Tesla meter per ampere. Okay. B is magnetic field strength measured in Tesla. So they'll ignore the second B on the next line. So magnetic force exerted on a charged particle per unit charge per unit second. I don't get it. Magnetic force is magnetic force. Magnetic force is force. I don't get it. The second B. No. I said ignore the second B. Ignore the second B. Ignore the second B. There should be this should have been F subscript B. This should have been F subscript B. So the magnetic force exerted on the charged particle per unit charge. Thank you. Yep. So when the diagrams here are telling us about current flow or in a current carrying conductor and in the presence of magnetic field. So this is horseshoe magnets. We have the north and the south pole, and as our tradition, the direction of magnetic field points from the north to the south pole. So this diagram, we can replace this diagram with the other ones where we see that our north pole is outside the spring and the south pole is behind the spring. And that means that the direction of our magnetic field is pointing into the screen. So when we have, so scenarios A and B are just the same. So now when we have a current carrying conductor in the presence of magnetic field and the current flow is 0, then the conductor will not experience a magnetic force as a result of current flow. But when we come to this other scenario in which current begins to flow upwards, when current begins to flow upwards and the direction of magnetic field goes into the screen, then we should expect magnetic force. And the magnetic force we should experience should be mutually perpendicular to the direction of current flow and also to the direction of magnetic field. So the direction of magnetic field is into the screen, current flow is upwards. Now, the magnetic force tilts to the left. So all those three lines should form, the magnetic force should be 90 degrees to the magnetic field and also 90 degrees to the direction of current flow. And you will have a maximum magnetic force when the direction of current flow and the direction of magnetic field are 90 degrees to each other. That is when you will have the maximum magnetic force. And that takes us to the definition that we have here that says FB is equal to QV cross B. Because the FB that you get here will be 90 degrees, we'll have an angle 90 to QV, and also have angle 90 degrees to B, which is the magnetic field. So magnetic field goes into the screen according to these diagrams, and current flow upwards. When current is flowing upwards, it's easy for you to picture it as charges are moving upwards. But if you want to think about it more in depth, and you want to say that the direction of current flow is opposite that of the electron flow, well, fine. But the conventional current has been adopted so that it's easy for us to think about something flowing, to think about the positive flow. Actually, it's the electrons that flow, but it's difficult for you to think about something that is negative to be flowing. It's not difficult for you to think about something that's something to be flowing from negative to positive. It's easier for you to think about it flowing from positive to negative. That is why we have it as conventional currents. It's convenient to think about. Yeah. So the last diagram we have here, we are now having a scenario where the current flow is now opposite the direction of the previous one. In this scenario, current is now flowing from top to bottom. As the direction of magnetic force will change because the V we have here, that is the velocity we had in figure C, has a direction that is opposite the V that we have in this. So if we'll talk about it in vectors, if we give it a velocity for C, then D will have minus of that velocity if we think about it in vectors. And you can see they are vectors. So now we'll move from thinking about charges and be thinking about current flow. We'll stop thinking about this Q. I will start thinking about I, which is current flow. And if we will need to remind ourselves, let's redefine this current I. I is equal to, is it the Q, right? the Q, the time, right? So for those that don't like seeing delta, D, and things like that, you can just say Q over T. You can still be forgiven. So just say I is equal to Q over T, and Q is equal to IT. Well, we'll manage it. So now, let's look at this as a segment of wire. This is a current carrying conductor having a certain length L. Now we are interested in fragments. We are interested in what is the equivalent of this QV cross B. I would prefer to say that this Q should be replaced with IT, right? Yeah, so if I say that let this Q in this expression be replaced with IT, just like our people from Greek would like it. Oh, look at me. I want to replace the Q with IT and I'm writing Q again. That is why I don't like coming here with an empty stomach. So let's write the Q as IT. And V, which is still the velocity cross B. T is time, B is velocity. Time times velocity. Oh my. Velocity times time. Do we need to start verifying jam results? So doing that will lead us to saying that instead of saying time and velocity, we can replace it with length component. Length and B. So I think it's convenient to move forward. And that's all we have here to say that IL cross B. And the L here is not just L, it's a vector. It has a direction. And that should lead us to knowing that when current is flowing, we are concerned in the direction of the current flow as far as we are interested in the effect of magnetic field on it. So what we have here is just similar to what we have here to say that a wire segment of arbitrary shape, that is the yellow line is the wire segment of arbitrary shape carrying a current I in magnetic field B experiences a magnetic force. That's expected. It's carrying current in the presence of magnetic field. So it is certain that it should experience magnetic force. So if we take this wire of certain length, we can break it into small bits. We can break it into small bits. Breaking into small bits, we can take this small bit and call it ds. Or we call it dl, since we are talking about the length now. S here is the length. So we can call it also dl. And the magnetic force that each of these segments will experience can be added together to determine the magnetic force that the entire length will experience. So we have one example here. Let me see if we have time for that. It says a straight horizontal length of copper wire has a current I. Current I equal to 46 ampere, 46 amperes. What is the magnitude and direction of the minimum magnetic field needed to suspend the wire, that is, to balance the gravitational force on it? So I would like to look at this question from the back, which says that what is the magnitude and direction of the magnetic field needed to suspend the wire, that is, to balance the gravitational force on it? To balance that gravitational force is the point of interest here. So then we should be interested. So what this is telling us is that a particular length of wire is carrying current, and instead of the wire to slip on the floor, it's now being suspended in the air because of the presence of magnetic field. Then what is the strength of that magnetic field that can suspend this wire? Then we should be interested in two things. The first is that what is the gravitational force that that length of wire is experiencing? And the second is that what is the magnetic force that that length of wire is experiencing? From basic physics, you should agree that for that length of wire to be suspended, then the gravitational force, which is meant to pull it downward, as balanced with the magnetic force that is suspending it. What that means is that gravitational force here is equal to the magnetic force. That is why it's standing up with here. I forgot my key at home. I should have walked up straight like this without touching the floor, such that my magnetic force will lift me up to balance the. If I had brought it, you start running away from it. You start seeing me in your drips. But you just, if I begin to walk like this without touching the floor, that means that fine, the force is pulling me down. Normally, the gravitational force is pulling me down, but there is another force that is balancing that gravitational force. So for us to determine that force, we should first start with determining the gravitational force that should have brought me down, which is the product of my mass and acceleration due to gravity. So that should be the force that is pushing me up for me to stay on that level. If that force is greater, I begin to move up. If it's lower, I begin to move down. When there is a net force, we have motion. What's the definition? The trade was good. Yes, so yes, there is definition. Just like the magnetic field because you are being to attract to repel from the tree. And doing that, the whole weight of the chain not rest on the rail. You have reduced friction significantly that to be able to move this. You can apply that. Come and show us like money. And just walk in here with reduced friction. So when we say magnetic or gravitational force, that should be the mass of this wire, which is 45.2 grams per meter. So we have to introduce another variable to say that, let's remove this one to say that the mass times a certain length, L, then times G, which is the acceleration due to gravity. Then we should also remember that FB is equal to, is it IL cross B, right? So the question is not, is saying that what magnitude, there is one phrase that I think we should take seriously, of the minimum magnetic field, this minimum magnetic field. So we should also remember that this is as good as saying IL B sine theta. So the angle between B and L matters a lot. When the angle between them is 0, the magnetic force will be 0. So for a certain magnetic field B, for you to have the maximum force, then theta must be 90 degrees. What that tells us is that when theta is changing, the magnetic force will be changing, even when the magnetic field is constant. And now, when we have the theta to be 90, that means that when theta is 90, magnetic field can be minimum for you to have a certain large magnetic force. So the trick is to say, for me to have this IL, B, and sine theta are multiplying themselves, I want a particular scenario where B will be the minimum. Then it's logical to say, let me make my sine theta to be maximum. So when my sine theta is maximum, which is 1, that is theta at 90 degrees, then I can now assume that sine theta is 90 degrees. Then we don't have to bother about theta anymore. We've known sine theta to be 90 degrees. Then the next thing to do is to talk about B, I, and L. So now the next thing to do is to equate the magnetic field, the magnetic force to the gravitational force. So we equate Fg to Fb, and that will now give us 45.2 L times G, where G is acceleration to gravity. Okay, I have a free space here. Fg equal to, come on, 45.2 times L times acceleration due to gravity. Should we call it 9.8 or 10? Like software. All newtons. And this is now being equated to ILB. I is 46, right? 46 amperes times that certain L again, times B, which is of interest. Oh, sorry, times B. So doing that, we don't need this Fg anymore. We've equated it to Fg and B. So then L can cancel L, and then we'll make B subject of the formula, and we will have the minimum magnetic field. What is it? Oh, thank you. Thank you. The mass is in grams. Thank you. So we have to convert we have to divide this by 1,000. Thank you. So we have to divide this by 1,000. Please, let me confirm. Yeah, so yes, then we'll be having the magnetic field at the SI units. Thank you for seeing that. Okay. Yes. Yes, when theta is 90 degrees, magnetic force should be maximum. Oh, I said minimum. Ah. Let me restate what I thought I said. I said magnetic, we want the minimum magnetic field that will make the magnetic force maximum. And a trick to do that is to set theta to the maximum, so that we will have the minimum magnetic field that will make the magnetic force maximum. No, you are not even to it. So let's talk about the torque on the current carrying coil. So a current carrying conductor can experience a force that makes it to rotate when placed in a magnetic field. I'm sure you still remember torque in physics 102. I think they will say when you are opening a tap or something like that, there is one force and there is one distance between that edge of that tap to the center of the tap, and they will now after now saying there is one moment of force like that. So forces in nature, they balance or they have the same units, they counter themselves, they add up as long as this force. So when we are talking about a coil in a magnetic field, it experiences force, just like we've shown in this diagram, where the current carrying conductors are experiencing forces. And the force, what do you expect force to do? To kick you out of rest, to set you in motion until there is a balance. So when current flows through a conductor in the presence of magnetic field, it experiences a force. And this we have said as QV cross B or IL cross B. The magnitude of that force depends on the magnitude of charge here. It depends on the velocity here, and also depends on the magnetic field strength here. Similarly, it depends on the current that is flowing through. Large amount of current should give us larger magnetic force. That is expected. So, and this application is used in many devices, even from measuring electricity. In the galvanometers, like we've seen before, in electric motors and alternators and many other applications, when current is flowing, the magnetic field, the magnitude of that current determines the magnitude of the magnetic force that is experienced. And the force that is experienced will cause motion. And that motion is what we measure in galvanometer to say, since it has moved this far, it is so amperes. It has deflected, the needle has deflected just a little. That means that tiny current has flown through the galvanometer and tiny magnetic force is experienced, tiny deflection is observed. So, but let's come back to talk because time is running low. So, okay, I think it's better I read through. A current carrying conductor can experience a force that makes it rotate when placed in a magnetic field. If a loop or wire is suspended in a magnetic field, the magnetic force produces a torque that tends to rotate the loop. The torque is responsible for the operation of a number of devices, including galvanometers and electric motors. For torque, tau is equal to NAIB sine phi, where phi is the angle between the normal of the plane of the coil and the magnetic field. So what this is telling us is that we can as well say it's something like NAI cross B, and we call it torque. The angle between the normal of the plane and the coil and the magnetic field. N is the number of turns in the coil or loop in the area, or loop of area A, carrying current I under the action of magnetic field B. So in the presence of a magnetic field B, when current I is flowing through, the torque depends on the strength of that magnetic field B. It depends on the current flow I. It depends on the area of that coil A. And it also depends on the number of turns. So when you are, when we're talking about a loop, you are taking a wire, you are rounding it, you are making it to form a circle or whatever shape, just to form a loop. When you have 5 turns of such wires, the force you will experience will be half of what you would have experienced if you have made the loop to be 10 times. So the number of the loops, they matter. So when you have 2 devices and they say they are doing the same thing, you lift one up, is lighter than the other, just like you are trying to lift your Chinko phone, comparing it with my iPhone, and you see that my own is heavier. The number of loops of the coils that have been used in my receiver, transmitter, and everything, they are complete compared to your own that they used 5 instead of 20. And they gave you a discount of 5,000 naira. So the point is that the number of loops determines the torque. So before we leave this page, there is also the magnetic moment, which is defined as mu coil, and it's defined as a product of the number of loops, the current flow, and the area of the loop. And it's measured in ampere meter square. Area is meter square, I is ampere, N is number, unitless. So this is the loop we are describing. It's having a certain area A. To calculate this area, it is A times B, right? Primary school area of a rectangle. A times B is the area. I'm sure you enjoyed your CA yesterday. I fulfilled my promise. I said it will be very, very simple. I said it, and I fulfilled my promise. I've marked a good number of scripts, and I fulfilled my promise. And let me make another promise. The examination will not be very, very simple. I don't like deceiving people. I tell you as it is. Okay. So when we think about this coil, or think about this coil, you know, the electron doesn't deceive people. So I try acting like the electron. So current is flowing around the loop. It's serving a certain area A, which is product of A, area capital A, which is a product of small a and B. Looking at this triangle from the side, if you can fix in your eye at this point, such that you are looking, half of your eye is above the screen and the other half is inside the screen, you'll be seeing a straight line. And that straight line you'll be seeing is this line. You'll be seeing a straight line of length B. You need to be a witch to see length A. All you will see from that side will be B. You cannot see A. So now we can see the length B on this side. And this from the top, we can see this as 1, 2, 3, 4. And from the side, you can see the edge of 2 and the edge of 4. And now, this triangle, so not triangle, this rectangle is something like this. Now, if you want to start turning it this way, so this is length A, this is length B. Why not? No, this is length B, and this is length A. And now, if you look at it, you should only see the length B. And look at this C. So now we want to start turning it about this angle. And then we're turning about this angle. So when we give point about this angle, the way they talk to in your primary, it should be product of force and the distance to the center. So now we should be interested in what happens at the edge, the force that is being applied at the edge here, and the distance to the center, which will be evenly divided by 2, right? We should be interested in the center of that triangle to be the axis where it goes around, then E divided by 2 should be the distance and the middle of that rectangle. That's a triangle. Middle of that rectangle to the edge. So some things that will, so to have the torque, we have, so now at this point, F2 is acting upwards at point 2. F4 is acting downwards on point 4. What is the torque? What is maximum torque? And we come to this expression to say that the torque is F2, product of F2, and the distance from F2 to the center, which is E over 2, plus F4, which is in opposite direction to F2, times E over 2. And what is F2? What is F4? F2 is F2 is equal to I L cross B, right? So, but in this scenario, you will see that direction of a magnetic field is, come back in. Direction of a magnetic field points from the left of the screen. The green arrows from the left hand side of the screen, the green arrows is the direction of the magnetic field, and it's pointing from the left to the right. And we don't need a prophet to tell us that the direction of those magnetic field lines is angle 90 to the direction of current flow here. The current flow is downwards. The magnetic field is to the right. Hence, the theta there is 90 degrees. Sine theta there is 1. So we don't have to stress ourselves with talking about sine theta anymore. Sine B, okay, sine theta, since theta is 90 degrees, sine theta is 1. So we can replace all this with 1, and we'll be left with ILB. And what is L? L here is the length of this line. It's the length of line 2, and that is A. So we can replace L here with A, and we'll be having IAB, which we have here as IAB and IAB. So when you add them together, you get IA small b, big B. So, and since small a times small b gives us the area, then we can replace small a and small b with area big A. Area big A. So the formulas we have in this square are very handy. Where that gives us mu coil NIA, we defined it here, torque, which is mu cross B. So the torque, which will be defined here as NIA cross B, is also mu cross B. So that means that mu is equal to NIA, which we have said like 5 times now. So when you have a scenario where the coil is constantly perpendicular to the magnetic field, it may have an angle. When it's standing this way, that's 0 because angle is 0. But when it's standing at a particular point, so we should now think about the general expression that will take into consideration the angle between the coil and the magnetic field. That is why we have the other stories we have here. But the maximum will be when the angle is 90 degrees and sine 90 is 1. So a general form, instead of talking about tau max to be product of current, area, and magnetic field, we'll be talking in terms of current, area, cross multiplied with magnetic field. So the cross multiplication will take care of the angle theta between the area A and the magnetic field B. Wow, 9 minutes to go. So now we have, let me see. Good. So I think this is the last slide. So from next class, I should be expecting Professor Obed to come and continue with the class, where you'll be learning more things about this magnetic AC circuits and the likes. So now, this example is saying that a rectangular coil of dimensions 5.4 centimeter and 8.5 centimeters. The first thing that should come to your mind here is a rectangular coil has a certain area. So the products of the dimensions should give you the area. Consists of 25 tons of wire, N is equal to 25. Carries a current of 15 milliampere. I is equal to 15 times 10 raised to the minus 3 ampere. So that's the information. Now, a 0.35 Tesla magnetic field is applied parallel to the plane of the coil. Calculate the magnitude of the magnetic dipole moment of the coil. So what is magnetic dipole moment? We really have to go that far. Do we have to get the formula for magnetic dipole moments? Magnetic dipole moments is mu, which is NIA. So we know N, we know I, and we know A. So easily we can determine the magnetic dipole moments. And the other question is saying, what is the magnitude of the torque acting on the loop? So, and what is torque? Torque is equal to IA cross V. IA cross V. We know I, we know A, we know B. But do we need to do anything further? What do we do further? You know, the reason why I'm asking is because this question is saying magnetic field applied parallel to the plane. It is parallel to the plane. Is that zero? This magnetic field is parallel to this plane, right? So is that zero? The magnetic field there is parallel to the plane. It's parallel, right? It's parallel to the plane, but it is forming 90 degrees to the direction of I. It's parallel to the plane, but it's forming an angle 90 to the direction of I. So we would actually add this to take it as we know I, we know A, we know B, and we know theta to be 90 degrees. So we can just multiply it up and have the torque. So I think we should stop here. So if you still have challenges, I still respond to emails. Feel free to send emails to PHY104 PHY104 at stu.ui.edu.ng. And the blog is physics104.wordpress.com. So I will update the blog and the YouTube channel today, tomorrow, and I'll still be responding to emails if you have any challenges via email. And if you have a problem that you want it to be solved and placed on the YouTube channel, you can also send such requests. If I see such requests, I can just solve it, make a video of it, and place it on YouTube. So I wish you the best. Bye-bye.